Okay, so I hope you could see the title, Integrals Yielding the Inverse Trigonometric Functions. Last meeting, we have covered everything up to the type 6 of trigonometric transformation. So for today, as I've said, I intend to finish 3. So we'll see. Okay? Please pay attention. If you think I'm very fast, you can call my attention. You can ask questions if there are questions. Okay? So when you speak of integrals yielding inverse trigonometric functions, simply put, the integral will have an answer which is an inverse trigonometric function. So as you can see here on the left side, you were given the derivatives or the differentiation formula for the 3 functions arcsine, arctangent, and arcsecant. And you see the derivatives in here. So this must be very fresh in your memory because you've just discussed this last semester. Okay. Now what happens in integration class is this. If you're going to integrate the derivatives of the functions that were shown to you in here on the left column, you will yield an answer which is the original function which you differentiated. So here in the second column, the answer or the derivatives of the function were integrated to give you back the function where they came from after differentiation. And as such, we say that these two processes, differentiation and integration, are inverses of each other. So if you're going to integrate this one, it will give you the arcsine. If you integrate this one, as you could see here, it will give you the arctangent. And the same is true in principle to the integral of this expression, giving you the arcsecant of u. It is very important, class, that you understand, just like any formula in integration, that the du you see here, this du that you see here, are the derivatives of the u in here. So the u in the first example is under the radical sign, so it's u squared. So you have to get the u by taking the square root of this u squared. That would be your u, or your function of u, and its derivative should be present in here, or should be complete in here. If not, you have to complete it. That way you can readily answer the arcsine of u. It's the same thing with the second here formula, 1 over 1 plus u squared. You're going to integrate it in terms of u. That yields tangent, or the arctangent rather, of u. And in this one, you just interchange the manner of subtracting in here in the arc sign. So instead of 1 minus u squared, you place here u squared minus 1. And before the radical sign, you should have the u. That should give you the arcsecant of u. These are the 3 main formulas for functions which, when integrated, will yield an inverse trigonometric functions. Now, why I say this is the 3 main formula, and you don't seem to be given here the integral yielding the arc cosine, the arc cotangent, and the arcsecant, right? It's because that whenever you know already the integral of this expression, and this expression, using the identities that were shown to you in your trigonometry in high school, you can already determine the arc cosine, the arc cotangent, and the arc cosecant. So you can see in here that the thing that separates the arc sine and the arc cosine is a constant, which is equivalent to pi over 2, or this is 90 degrees in degrees. The same thing with the arc tangent and the arc cotangent. So you see, you have here a pi over 2, or that's 90 degrees as well. Same thing with the arc secant and the arc cosecant, which is pi over 2. So if asked what will yield the arc cosine, the arc cotangent, and the arc cosecant, this will be the identities that will bring about those 3 other inverse trigonometric functions. But in terms of integrals, we only have these 3. So we have the arc sine, the arc tangent, and the arc secant. If you know this, and let's say you want to get the arc cosine, the arc cotangent, and the arc cosecant, you go back to these identities. Okay, so this was shown in here that they differ from each other by a constant only. So that constant is the same to all our pairs here. It's pi over 2. If you're going to ask me what are the three main formula, integration formulas, this would be the 3. Why I say main? Because there would be instances, class, that you will have here a real number other than 1 in the case of the arc sine. The same thing in the case of the arc tangent. This could be any real number. I'm pointing to 1. I hope you could see my cursor. So this could be also a real number. In the same way that this could also be a real number. Whenever you are given such particular integral, don't panic why it's not 1. Why is it any real number? Because you're just going to modify a little. You're just going to modify a little these three main integration formula that you were provided. How little is the modification? So let me scroll down. I will not focus on the differentiation, on the derivation rather, but I'd like to focus on the formula itself. So allow me to annotate so you will see. So in here, instead of a 1, this should have been a 1 in the main formula minus u squared, still under the radical sign in the denominator. So now you have a squared where a is any real number. So to save us some time, whenever you have an a here or any real number, all you have to do is determine the a. That a is actually the square root of that real number. And whatever the value of that, instead of just simply answering the arc sine of u, whatever the u here is, you're going to write the arc sine of u over a. You have to make corrections or accommodate the constant here other than 1, which you are subtracting the u squared from. Okay, so the only difference of this formula from the main formula that was shared to you is this division by a in the argument of the arc sine. Okay, now if you're given something similar to this scenario, this time you're not given a radical sign in the denominator, but you're given simply the sum of the squares of a real number and u squared. Now, this could have been a 1 plus u squared, which is easily written as the arctangent of u. Excuse me, the arctangent of u. Now, in this case, since you have an a squared or real number here, just determine the a. You take the square root of this particular real number and then follow this formula. The original formula for the integral yielding the arctan function is simply the arctan of u. But whenever you have an a squared here added to the u squared in the denominator, you have to add this one, the 1 over a, and the argument of your arctangent should have also division by a, just like in the arc sine. Okay, you just add this one, the 1 over a, to the arctangent, and instead of just having the plain u, you divide it by a. That is in the case when your denominator is 1 divided by a real number plus a function that is being squared. Okay? Can you follow? Okay, so no reaction. So I hope everybody can follow. So now it's the same thing actually again to the arc second. Now the original form here is u square root of u squared minus 1. Now you have a real number here. So just like the arctan that you have here on top, you have to add in the formula 1 over a. You still have the arc second, but the denominator should accommodate the a in the argument of the arc second. So instead of just arc second of u, you write arc second of u over a, and then you multiply it by 1 over a. So that's the reason why a while ago I said that you only have 3 main formulas for integrals yielding the inverse trigonometric functions. The others will just follow as long as you understand when you need to multiply by 1 over a and when you need to divide the argument of your inverse trigonometric function by a. So when? That is when you have, instead of the 1 in the standard or in the 3 primary formulas, you have any real number. When I say any real number, it could be a fraction, it could be a decimal, it could be a perfect square, it could not be a perfect square, as long as it's not negative, because you cannot take the square root of a negative number. Now, don't mistaken me when I say negative, this one negative. No, I'm referring simply to A. So your A has to be positive after you have taken the square root of the real number that was placed together with the u squared expression. Now, do you have any question to the formulas before we go to the specific examples? Okay, so I think there's none. So we'll proceed to the examples below. You see this one? This could have been an arc sign only. Could have been. Why? Because this is not 1. So it follows that your A here is 3. You take the square root of the 9. So simple. Arc sign of x over 3. Instead of simply writing the arc sign of x. Now your u in this case is x. Because x squared, it's x squared here. And the du of that is dx. So no problem in terms of the derivative. It's already complete as written. So this is your answer. Now in here, we just modify a little what you have in here on top. You still have a here equal to 3 because square root of 9 is 3. But in here, your u is 2x. For x squared, you take the square root is 2x. So the du of that is 2dx. Since you only have dx, you need to place here 2 to complete it, and you place 1/2 before the integral. So you can see that you already have 1/2 here. The arc sign of the u, which is 2x, divided by a, which is 3. So very, very easy. As long as you understand the form and the use of the formula. Now, here in number 3, I'd like to scroll up a little. Oh, sorry. Here. It is. Okay, here in number 3, it's quite similar to the first 2. Your a is still 3. Your u is x minus 1. Okay, because you have it squared. So your du is dx. So no problem. You have already the dx. So same thing. Arc sign of u, this time it's x minus 1 over a, which is 3. Now, what if your function is not a polynomial like the x squared or 2x squared, something like that? It's a function in itself. So just the same, always identify the a and the u. So here in the fourth example, your a is 2, square root of 4. Your u is sine x, the square root of sine squared x. The du of this is cosine x dx. That's the purpose of this entire expression here. It is the du. It's just the same. You just apply the formula. You will have in form here an integral yielding the arc sign. So you see this one of u. What is the u? The sine x divided by the a, which is 2. Do you follow? Another example is number 5. So this time, you have a non-perfect square for your real number. So your a is the square root of 5. No problem with that. You can write it as square root of 5, or you intend to find the exact value. It's fine. Your u is e raised to x, because e raised to 2x, when you take the square root of that, that's e raised to x. The du of this is e raised to x dx. So the purpose of the e raised to x here is to represent the derivative of the u. The same thing, you have the answer, the arc sine of u, which is e raised to x over the a, which is square root of 5. Any question? Okay, I hope it's clear. There is no question. We proceed with 6 and 7. Now, this time we'll have a plus with no radical sign. So what is this? You have to think, what is this? This must be, you're not yet sure. So you have to identify what's the a and what's the u. So your a is 5. Your u is x cubed. The du is 3x squared dx. You differentiate this. It seems like you lack the 3 in here, and you have to place 1/3. That way, you did not alter your original integral. So this entire expression represents the derivative of the u. That's it. Arctan is a 1 over a when your x squared, or when your u squared rather, is added to a real number, which is other than 1. So it has to be 1 over a. That's as per formula. That's 1 over a arctangent of u, which is x cubed over a. Where is this 1/3? That 1/3 is this 1/3 here, which should compensate for the presence of the 3 here for the derivative of your u, which is x cubed. Do you get it? Another scenario is for this one. So you have a form which is u squared minus a squared, and this is the u. So you check. So your a is 6, your u is 2x, your du is 2dx. So you don't have the 2, so you place here 2. You place 1/2 outside. Now in terms of form, what should be placed here is just the u. And what is the u? That's 2x. So you have more than this 4 here. You should take out the 2, or you divide it by 2. So you have another 1/2 here outside. You only need the 2x here. And that's it. You will have 1 over a, which is 1 over 6. Arc secant of u, which is 2x over a. And you have this 1/4. So this 1/4 is this 1/2 and this 1/2. You only set aside 2x here. So meaning you have to factor out the other 2. So that would be what? This 1/4 here. So if you simplify, that would be 1 over 24, the arc secant of x over 3. Okay? That would give you a 3 here plus c. Do you get it? Any questions? Okay, not. Here my markings. We'll go to, I think there's a last example here. Now this one is for the arc secant. You're not yet sure whether this is an arc secant, so you have to check. So here you have u squared. So u then must be e raised to x only, because this must be u squared minus a squared. So your a is 4. Now the du, if your u is e raised to x, is e raised to x dx. Seems like you don't have it here. So you introduce an e raised to x here. And so as not to alter the entire integral, you should have an e raised to x also in the denominator. Notice I did not write it before the integral. Why? Because this is not a constant. You can only factor out, you can only write before the integral constants. If they are not constants, you are to write them after the integral. Good in this case because this e raised to x will be needed. That way this will conform. So this will conform to the form u square root of u squared minus a squared. So the e raised to x, which you place in the denominator to compensate for placing e raised to x in the numerator, now has a purpose. The purpose is to make sure that the form of the integral yielding an arcsecond is complete. Okay, now it's in the form du over u square root of u squared minus a squared. So just the same, you have 1 over a. The a is 4. Arcsecond of u, which is e raised to x over 4 for the a, plus c. Do you get it? Do you have any question? No question? Okay. If there are no more questions, we'll proceed, class, with integration by parts. Okay? That's a short topic for integrals yielding the inverse trigonometric functions. I haven't yet populated your canvas regarding your problem set for such. I will just have it populated anytime today. Anyway, you're given 2 weeks for compliance. Now, you have a lot here, so make sure that you practice. Now, we go to this topic here, integration by parts. This is very, very useful in the case of SHE because in your professional subjects, you will not only be integrating standard expressions, but you will be integrating wherein you have a combination of functions. A combination of functions meaning you can have a polynomial and a trigonometric function, a polynomial and exponential function, an exponential function and a trigonometric function, and so on and so forth. It could only be handled using integration by parts. Okay? Let me just check what is written here in the chat box. Okay, it's okay. They just access the recording. Okay, anyway, I always have a recording. It's noted. Thank you. Now, when do you use integration by parts? If you are certain that for integrals yielding the inverse trigonometric functions, they will have radicals in the denominator, or in terms of form, it should be 1 minus u squared or u squared minus 1 or 1 plus u squared, something like that. There's an indicator in terms of the form. Now, for integration by parts class, there's also an indicator. I mentioned it already a few seconds ago. When you have a combination of functions in your integral, you use integration by parts. The functions that I'm referring to are this one. They are either the assigned as, let me just annotate. They are either assigned as the u or the dv, the rest. Okay. Now, how do we process an integral which has a combination of functions? What we initially do, class, is identify what should be our u. And of course, the rest of the expression will be the dv. Now, normally what is suggested, let's say for example, you have a polynomial multiplied to a trigonometric function or an exponential function or an ln function or something like that. When you have a polynomial class, most of the time it is assigned as the u. Okay, this one, it is assigned as the u. I will show you later what will you do with the u and what will you do with the dv. The rest of the expressions that you see in your integral after you have already assigned the u is of course your dv. But whenever also you choose for the dv, make sure that this could be integrated. What do you mean, Miss Ali? For example, you already chose a polynomial, let's say x squared for your u. And then the remaining expression is ln x dx. Sample lang. ln x dx, that's the remaining expression. Can that particular expression ln x dx be integrated? If the answer is no, then don't choose that to be your dv. You always make sure that the remaining expression after you have already selected the u could be integrated. If not, you switch it. So the dv that is left, which is not integrable when you separate it from the u, now will be your u, and the u will be now your dv. I'm sure if it's a polynomial, there's no problem because it could be right away integrated. Now, how do you ascertain, or what makes it sure that what you're doing is correct? By experience and by discovery. If you are practicing to solve integration by parts, you would know that I will have to do by parts, and this will be my u and this will be my dv. Okay, there is no best teacher in this case except practice and experience. So just like they say that the best teacher is experience. So you practice, that way you know well what will you assign as the u and the dv. But that's the suggestion. If you have a polynomial, assign it as the u, the rest of the expression there is dv. You don't select a dv that cannot be integrated right away. So if that is the case, you switch. If it cannot be integrated, you switch the dv and the u. Okay? Now I'll clear my markings here and go straight to the examples. Okay? I'll write the answer in here. Now, I'll use this one. You are given sine x dx. I'll write it here though it's there already. Now, your u is x because it's a polynomial. Sorry class, we'll just use a different color. Your u is x, the du is dx. dv, of course, will be the rest of the expressions here because you already assigned it as the u. So your dv is the sine of x dx. Now, can this be integrated? The answer is yes. So you don't have any problem, proceed. So the integral of sine x dx is equal to, so you integrate this side, you also integrate this side. That will give you a v here. And this one will give you the negative cosine of x. Integral of sine of x is negative cosine of x. Now, I teach my students the cross, shall I say, this particular form of processing, although you can memorize the formula. It's uv minus the integral of v du. That's how we process by parts. uv minus the integral of v du. Where is it written? It's here in your notes, so you can see here. u dv is equal to uv minus v du. Okay, whenever you intend to use by parts. But I use this one because I find it easy to do. And I will not have a hard time memorizing formula. When I write it in this manner, class, I place the u here, the du in here, the dv and its corresponding v in here. Then I cross. That's my first term, uv. So that would be negative x cosine of x minus the integral of v du. Cross, drop. Cross, drop. That's the form. So minus, so I have minus the integral of v du. You get the product of this. So this is negative, so that makes it positive. Integral of cosine of x dx. So the answer for this integral, the integral of x sine x dx, is actually negative x cosine of x and the integral of this, which is sine of x plus c. That's it. Cross and drop. You write the u, opposite is du. You write the dv, opposite is v, and you do this. Or if you don't have any problem memorizing formula, then go. It's uv minus v du. uv minus the integral of v du. That's our formula for integration by parts. In this case, you have a polynomial and a trigonometric function. So this is the technique that you will use. Do you get it? Okay, sige. You're silent, so I will just go on unless you have questions. Okay, we go to the rest of the examples here. Okay. Now this one, you only have one integral, integral of the ln of x dx. This is the one I mentioned a while ago. you cannot assign the ln of x dx as your dv because there won't be any u left, right? So then, your u must be the ln of x. I'll write it here so you will get accustomed to me writing it. Your u is ln of x. Your du is dx over x, right? The dv, of course, is the remaining expression. The dx is the remaining expression. So dv is dx. So if you integrate both left side and right side, that will give v equal to x. Then uv minus v du. Cross. Sorry. So you have x, ln of x, minus the integral of this, x dx over x. So you cancel this, x ln of x minus dx is x plus c. So that's the answer that you're seeing here. Okay? Now, this one is better because this is the one that I mentioned a while ago. You learn by doing. What do you mean by that, Miss Ali? So, let's say, for example, you assign u as the x. Example lang. The du of that is, of course, the x. Of course, the remaining expression, you have no choice. You have to assign it as ln of x squared dx. Question, can you integrate this? Can you integrate ln of x squared dx? The answer is no. You cannot integrate this. So this is an exception to the usual way of doing it, that whenever you see a polynomial, that's your u. And the remaining expression is the du. So you interchange class. There's nothing wrong with changing your mind in the middle of your solution, because you cannot insist on assigning this as the dv because you cannot integrate this. So you change your mind. So you change your mind. You erase. I change my mind. So I will do it the other way around. So this time I will have, where is it? I will have my u as the ln of x squared. Then my du is derivative of the u, 2x over x squared. Or simply put 2 over x. Then the remaining expression x dx is the dv. The dv is equal to x dx. Can you integrate? Of course, that's very easy. That's just power rule. So your v is equal to x squared over 2. Then you do the uv minus v du. So you have this. So your first term is x squared over 2 ln of x squared. That's uv. Minus the integral of v du. So 2x or 2 over x times x squared over 2. So the 2's will cancel each other. This one will cancel. You have the remaining x dx. By the way, I missed to write the dx here. There should be a dx. So you have x squared over 2 ln of x squared minus x squared over 2 plus c. Wait, why is this just x squared? Maybe there's a typo error. Oh, it's just ln of x here. It should be ln of x squared. So this is the correct answer. When you differentiate the u, it's 2x over x squared. You cancel the x's, it's 2 over x. 2 over x times x squared over 2 for the integral of this will cancel the 2's, cancel the x, leaving you with the x. So it should be like this. In here, there should be an over 2. Do you have any question? No question? Okay, good. I'm happy my students are there. And du should be 2 dx over x. Yes. Yes, it should be, I will write in red. So this should be, John Mark, your du, I'll write it here. After simplifying is 2 dx over x. One more question. No more questions? Okay, then I will proceed. So we'll clear the markings here. We'll have here this one. This one first. So you assign your u to be x. Du is dx. dv is the rest of the expression. E raised to x dx. V is e raised to x. Integral answer should be x e raised to x minus the integral of e raised to x dx. Cross and drop. So you have x e raised to x minus e raised to x plus c. Okay? Question. The second integral here is quite a challenge. This is when you will do double by parts. What are you saying means double by parts? So I will use the Jamboard to illustrate why it's double by parts. By the way, there should not be any dx here. Only one dx. Okay, it's the integral of x squared cosecant, or rather cosine of 2x dx. Okay, I'll clear my markings here. X squared and cosine of 2x. You share. I can't find my Jamboard class. Wait, ha. There it is. Okay, share. Okay. I hope you can see the Jamboard. The integral that we're talking about is the integral of x squared cosine of 2x dx. So we will assign our first u. Your u is x squared. The du is 2x dx. The dv will be the rest of this. Cosine of 2x dx. What's the v? Integrate this, you need to introduce the 2 here. You should have 1/2, then you can integrate. So this would be 1/2 the sine of 2x. Okay? We need to complete the derivative of the u in the cosine function. So that's the reason why you have a 2 dx here and a 1/2 before you integrate. If you do the crossing and dropping, so you have that and that. So you follow that. So you have here, I will now write this is equal to product of this. So you have 1/2 x squared, the sine of 2x. Okay, uv minus v du, these two. So 1/2 and the 2, you get rid of the 2's. You have minus the integral of x. You have this x here and the sine of 2x dx. See? Now, what will happen? You do again another integration here. Okay, you do another integration. So I'll use a different font. We'll use green. So here you will have a different u. So your u is x. The du is dx still. The rest of this will be your dv. Your dv is the sine of 2x dx. Your v is equal to 1/2 cosine of 2x. Just like what happened here. Now, this is sign, so this should be negative. So, erase ko anay. Isulot na siya. So, you'll have here b equal to negative 1/2 cosine of 2x. Then, we'll use the cross and drop again. Cross and drop. Okay? Now, I will copy this and this. So, the integral of x squared cosine of 2x dx is equal to 1/2 x squared, the sine of 2x, I copied here, copied, and the corresponding answer of this another integral. So that would be minus. So minus uv, 1/2 x cosine of 2x, x cosine of 2x, minus the integral, but it's minus here, so that would be plus. And you have this, plus, you have negative 1/2, you have this, integral of cosine of 2x dx. So last line, you have 1/2 x squared sine of 2x minus 1/2 x cosine of 2x. Now, what's the integral of this? It will need another 2 for the derivative of the 2x. So that would be minus 1/4 the sine of 2x plus c. Now, this is an example wherein you have to do double by parts. What tells you that you will do double by parts? It is the what? The degree of the polynomial here tells you how many times you will do by parts. So if this is cube plus, you will need another by parts here. So instead of having only 3 terms in your answer here, of course not including the c, you will have 4. Okay? So that's what is tedious when you have a polynomial of degree higher than 1. When it is your u and the rest would be your du. Question is, Miss, if we will interchange, what will happen? Like, I will make cosine 2x as my u and x squared as my db. X squared dx as my dv. What do you think will happen? You will even have more problems to come because you cannot finish the integration. It will be a process wherein you will have a bigger and bigger degree or a higher and a higher degree result for your polynomial. So whenever you have a pair of a polynomial and a tangent function, or a polynomial and an exponential function, always assign the u for the polynomial. You can do it at home. You try interchanging this one and see what will happen if you can lessen the number of integration. It will not lessen the number of integration. Okay, or it will not decrease the number of integration. Do you have any questions here in this particular example where we have to do double by parts? I hope you're still there, huh? Anyway, so this is double by parts. Now I will go back to our slides, our document rather. Okay. Okay, you have here double by parts. Now we go to, this is the answer. Now, what about this one? E raised to x sine of 2x. So, there's no polynomial. One is exponential and one is trigonometric. What do you think will happen if this is the case? No polynomial, both are different functions. This is what my students would call then in our language, balik-balik. How balik-balik is balik-balik. Okay? So we go back to our jumper, then I'll show you how balik-balik is it. Okay. integral of e raised to x sine of x dx. You will do balik-balik for this whether you use u as e raised to x or u as sine x dx. Now, I leave that to you to as an exercise to check what will happen if you interchange. But you will still do balik-balik as what my students would say. Now, what is balik-balik here? So, just the same, we will assign the u and the dv. In my case, I'd like to assign u as e raised to x. Of course, I will have the du as e raised to x dx. dv is the sine of x dx. v is equal to negative cosine of x. So I go back to what I have on top. Okay. Cross and drop. So I will have negative e raised to x cosine of x minus the integral of this, that makes it plus integral of e raised to x cosine of x dx. See, you will do another by parts. This one. So another u e raised to x, the du is e raised to x dx. The dv will be the rest, cosine of x dx. The v is sine of x. Cross, drop. What will happen? I'll go back to what I have there. Integral of e raised to x sine of x dx is equal to negative e raised to x cosine of x, and this one giving you this one, plus e raised to x sine of x minus the integral of this, minus the integral of e raised to x sine of x. Now you know why it's balik-balik. You see the reason why it's balik-balik. This and this are the same. So you transfer this on the left side. If you transfer, you will have now 2 integral of e raised to x sine of x dx is equal to negative e raised to x cosine of x plus e raised to x sine of x. Isn't it we're after the integral of this alone? So we divide the entire expression by 2. Therefore, the integral we are after, e raised to x sine of x dx, is equal to 1/2 e raised to x times. I'd like to factor out the e raised to x. So this one is positive. I'll write it first. Sine of x minus cosine of x. So this is the answer to this integral. After you did balik-balik, because you in the process of doing by parts, you went back to the original given integral. So you have to transfer it on the left side. That way you can get the integral that you want to answer. Or you can get the answer to the integral that is given to you to evaluate. Any questions? No questions? Okay, you can have a 10-minute break. Our class ends at 5:30. So my time now is 4:33. Come back after 4:43. Okay, I'll stop sharing for now. And I will just pause this one. Sharing my screen again. Okay. The rest of the example class, I have covered already 6 of the 10 examples here in 5 parts. The four examples I leave to you to read. Anyway, it's complete. Should you have any questions, you just ask me or you message me should you need to be clarified with any of the solution that is given here. That way we can go to the next topic, which is the hyperbolic functions. Anyway, they're just formulas. So all you just need are formulas. They are not as complicated compared to integration by parts. Now, I have here, class, a summary of formulas. Actually, some were already shared to you in the topic of trigonometric transformations. These are formulas that are ready to use. If you are a person who has no problem with memorizing formulas, so that you can right away answer a given integral using these pre-derived formulas. So actually, these formulas came about after using integration by parts to the integrals that you are seeing. For example, you're given u raised to n ln of u du. If you process this using the integration by parts where n is any real number, you will have this particular answer. So to simplify the process or decrease the time in processing this by hand using integration by parts, you already have a ready-made formula to use. It's the same thing with ln of u raised to n du. So this is a ready-made formula for you to use. Same thing with u raised to n e raised to au du. So this could be x raised to n, e raised to ax, where a is any real number, dx. So this is your ready-made formula for that. Same thing with u and cosine, u and sine. You already saw the examples because we have that. Then we have the e, the exponential function paired with a cosine. We have the exponential function paired with the sine, already shared to you. Also, the cosine of u raised to n, which can be processed using trigonometric transformation. This is case 1. Same thing with sine u du, where sine is raised to n. Now, these are ready-made formulas. Some formulas, class, have limitations. So, in this case, n should not be equal to 0. And n here also should not be equal to 0, because if it's 0, automatically that would be 1. Okay? In here, you have another sine u, cosine u function where the sine and the cosine are raised to exponents m and n. In our trigonometric transformation, the m and the n are specified, well-defined, whether it's odd, even, positive, or any real number in here. It's not that specified anymore. So meaning m here could be a fraction, m here could be a whole number, because there's no limitation to the use of this formula. The only limitation, class, is this: if, let's say, for example, the m that is given you here will not ensure that you can process this integral of the sine of m minus 2 or the sine of u raised to m minus 2 times the cosine of u raised to m. Okay? So, as much as possible, it would be better if your sine here and your cosine are whole number and positive exponents. Okay? So, by the way, it's in here. I missed looking at the limitation. So, your m should be greater or equal to 2 for this particular formula to work, and n should be greater or equal to 0. Okay? For you to use that formula. In here, you have the tangent, cotangent, secant, and cosecant. Then you have the sine AU, sine BU. This was already shared to you. This is type 6, sine, cosine, and cosine, cosine. Okay? And you have here the U and the arc sine, the U and the arc cosine, the U and the arc tangent. You have here the conditions that have to be noted. That way, these formulas here, the last will work. Okay? Question. Chat box. Miss Pico is experiencing power interruption. Okay, thank you, Carlos. Now, these are the formulas that were pre-derived using integration by parts. So that's how useful it is. Okay? Now, we go to the next. I don't think we can finish the topic on, sorry, techniques of integration because of the 1 week. We had 1 week of health break, so we will be lucky. We will be not finishing that topic. Anyways, we'll just see what we can finish. Where was it? Okay, here we are. Integrals involving hyperbolic functions. Take note, when we say involving, the integral is a hyperbolic function, not that it will yield a hyperbolic function. Okay? So integrals involving hyperbolic functions. And before the hyperbolic integrals were given to you here as a formula, you have this so many identities concerning the hyperbolic function. So these are the identities that you need to take note of. Okay? It would be best if you have a summary of all these formulas which you can look to whenever you're given a quiz or an exam. Okay, anyway, when you take the board exam, you have your, by the way, during the general engineering day, that's day 3, you don't have your handbook with you. So meaning, if you can't memorize this, should this be given, you just have to derive this on your own. Okay? These are identities involving hyperbolic functions. So take note of this. You may find them useful in simplifying your given integrals prior to evaluation. Okay? Our main concern is the integrals of these 6 hyperbolic functions. Comparable actually, it's quite comparable to the integrals of basic trigonometric functions like this. The integral of the hyperbolic sine is the hyperbolic cosine. The integral of the hyperbolic cosine is the hyperbolic sine. So both are positive. In the trigonometric function, the integral of sine u is negative cosine. In here, it's still positive. For the integral of the hyperbolic secant, it's the tangent. So just similar to the trigonometric function. The hyperbolic cosecant of u squared is negative cotangent. So similar. The hyperbolic secant, hyperbolic tangent. Now here, they differ in the sign. Because in the trigonometric function, this is positive secant u. In here, it's negative hyperbolic secant u. For the cosecant u, cotangent of u, or the hyperbolic cosecant u, hyperbolic cotangent u, it's negative hyperbolic cosecant u. So if these 6 formulas is to be compared to the 6 basic trigonometric functions, their integrals, the only difference is in here and in here. The rest are the same because this in the integral is negative in the trigonometric function rather, and this one is positive. The rest are the same if they are not hyperbolic functions, if they were just simple trigonometric functions. The way you integrate it, the principle behind is similar with trigonometric expressions and the rest of the formulas that were shared to you. Just make sure that the derivative of the u, the argument of your hyperbolic function is complete. So it is here du. So it's not as simple as du, especially if this argument of your u is not just a simple x, where you can have the dx. If it's x squared, then it should be a 2x dx here for your du. Okay? For you to be able to answer a hyperbolic sine of u. Let's pick 3 examples here. The rest you can read. That way we can go to inverse. Okay? If we'll end before 5:30, I will end you. That way you can rest. Now, hyperbolic sine of 1 minus 2x dx. Your u here is 1 minus 2x. So the derivative of that is negative 2 dx. In that case, you need to multiply here by negative 2 and place here negative 1/2. So you have your negative 1/2 hyperbolic cosine of 1 minus 2x plus c. It's easy, actually. All you have to do is take note of the formula. So hyperbolic sine yields a hyperbolic cosine. Now, wait. Negative. Okay, correct. It's negative 1/2. Any question here before I go to the second? Okay, what about the hyperbolic cosine of the square root of x dx? So the challenge in here is this, the u of your hyperbolic cosine. So it's the square root of x. If you will differentiate this, this would be 1/2 x raised to negative 1/2. The reason why you have here 1 over 2 square root of x dx. So that's the purpose of this square root of x here in the denominator. It lacks the 2, so you place 2 here. That's 1/2, so there should be a 2 outside. So hyperbolic cosine yields a hyperbolic sine. So you have 2 from here, hyperbolic sine of the square root of x plus c. So exactly, the treatment is exactly the same as that for the basic trigonometric functions and their integrals. Questions? Let me look into, okay, the one that could fit in my screen. So in here, you have the hyperbolic cosine squared of the quantity x minus 1. And you have here hyperbolic sine of the quantity x minus 1. We know that the hyperbolic cosine and the hyperbolic sine are related in terms of one being the derivative of the other. We know that. So we can use power rule for the hyperbolic cosine here when its derivative is in here already. You can see adding na here derivative of the hyperbolic sine of the quantity x minus 1 as written here. Or it's complete. So you can use power rule for this. So you will have the hyperbolic cosine cube of x. You use power rule for this one divided by 3. Because the purpose of this hyperbolic sine of the quantity x minus 1 dx here is for the derivative of this. So this is like u raised to n, for n being 2. So power rule. Okay? Now for this one, you could see that you have the hyperbolic second squared of e raised to x. We know that this one is readily integrable. The hyperbolic or the hyperbolic second squared, it will yield the hyperbolic tangent. But we need to ensure that the u of the hyperbolic second squared is in here. So you have e raised to x. So the du of that is e raised to x. There's an error here in typing class. That should be dx. It should be e raised to x dx. So then you are simply getting the integral of the hyperbolic second squared of e raised to x, which is the hyperbolic tangent of e raised to x. Let's see. Okay? The hyperbolic sine of x divided by 1 plus hyperbolic sine squared of x can be first simplified before evaluating the integral. This 1 plus hyperbolic sine squared of x is hyperbolic cosine squared of x. You may wonder, where is this miss? It's there on top. In here, I've shown the derivatives and before the derivatives and the integral, you were given the identity. So please review those. Okay? You have this identity here. The equivalent of that is the hyperbolic cosine squared of x. Now, if you split the hyperbolic cosine squared here in this manner, this will be your tangent. Your hyperbolic tangent, and the 1 over hyperbolic cosine is the hyperbolic second. this one yields right away a negative hyperbolic secant of x as per formula. So you just have to, again, use the identities here. So of course, we're not expecting you to memorize everything all at once. So that is what I'm saying. You should have a notebook, some sort of notes, because students before the pandemic during face-to-face have notes. I hope you also have notes. You don't rely on what you can click there in front of you and in your computer during quiz, because your notes would really be very useful. Once, because if you already have everything summarized, you alone would know where to find what you want to find. Or you can easily find what you want to find because you have organized it already. So my suggestion, organize all your identities, derivatives, and formulas. That way, it's so easy for you to go back to when the need arises. And it will also aid in your easy understanding, because you don't, I used to say this to my student, you don't ukay baluskay your notes because you have a disorganized notes. All the more in your case now class that you should have organized notes, because we don't see each other face to face. And I can only empathize much for you because it's really difficult to learn online without the notes. So you make your own. Hey, if you rise up above the challenge of this pandemic, you'll be performing even better than those that have face-to-face classes. It's actually all, it boils down all to your decision on how you're going to um, rise up above your challenge. Okay? So I hope the 5 examples class will do for the hyperbolic functions. That way I can go to the inverse hyperbolic functions. Okay, anyway, they are all formula. So in here, you have to read 4 more examples. Okay, here. The inverse hyperbolic is somehow, look at that. There's just so many myths. That's why the reason why you should have a summary of formulas. It's somehow similar to the integrals yielding the inverse trigonometric functions. This one would have been a arctan of u if we don't have the radical sign. Now, since you have u squared plus 1 under the radical sign, it's now the arc hyperbolic sign of u. Okay? The derivatives are in here, by the way. Now, the same set of formulas that you have encountered in your differential calculus, same here that you will find, because anyway, the two are just inverses, as I keep on emphasizing. So this one, what is its equivalent in the trigonometric function? If I have here the u, this would have been the arc secant. I don't have the u in this case, so it is simply the arc hyperbolic cosine. So take note, di magpanik nga wala na di u how. Dapat may u para mag-arc secant ako. You have a formula here. So without the u, it is just the arc hyperbolic cosine of u. Now, isn't this tangent supposed to be, if this is plus, arc tangent? Now, if it's minus, it's the arc hyperbolic tangent or inverse hyperbolic tangent of u. You can even answer also that it's the inverse hyperbolic cotangent of u. Whether any of these two is acceptable for this integral. Now, look what happened here. In the inverse trigonometric function, this should be u squared minus 1. What happened if you interchange? It's now negative arc hyperbolic secant of u. So we have the negative here. Because if it's u squared minus 1, it's arc secant of u, not arc hyperbolic secant of u or inverse hyperbolic secant of u. Now in here, plus, it should have been, by the way, so ligid siya dapat u squared minus 1. In here, it's square root of 1 plus u squared, and then you have the u outside. So it's the negative of the inverse hyperbolic cosecant of u. All about the formula. It would have been easy if the formula is not as complicated as you see them, but understand what's your u, understand the derivative of your u, and apply the formula, and you have it here. Do you have any questions before I go to the examples? So you have here class 6, 5 rather, 5, because the hyperbolic, the inverse hyperbolic tangent and hyperbolic cotangent are just the same in form, referring to their integrals. Now, you have here all-in-ones. What about if they are not 1? They are any real number. 1, 2, 3, 4, 5. These are your 5 primary formulas, and these are the other 5 derived formulas from the primary. Here. So it's in here. It's already simplified. You can see here. Now, if you have u squared plus a squared, which have been a simple hyperbolic, inverse hyperbolic sign, if it would have been 1, now it will be hyperbolic sign as well, inverse of that is, so arc hyperbolic sign, but you should also have the u over a plus c. Or, this is what I find cumbersome with hyperbolic functions because class pwede siya duwa ka answer. So you can answer in terms of another hyperbolic or inverse hyperbolic function, or you can answer in terms of the ln. Okay? So you have to really write a summary of formula for all of this. Okay? Now in here, you have u squared minus a squared would have been inverse hyperbolic cosine of u. So this one now would be inverse hyperbolic cosine of u over a. And treatment is exactly the same as that in inverse trigonometric functions. So the original formulas were just multiplied by accommodating the a's, which are other than 1 in this case. Okay? So in here, you have this one. So it's either an inverse hyperbolic tangent or inverse hyperbolic cotangent. Now the argument has been divided by a, and these two inverse hyperbolic and cotangent and inverse hyperbolic tangent functions are multiplied to 1 over a. You can have this alternative formula in terms of the ln, which I have summarized in here below. I suggest so that for now, since you're just starting and nobody can expect you to memorize everything, stick to the relationship between hyperbolic functions. So you may add this later on if you are already well versed on the use of the formula. Now in here, you have supposed to be inverse hyperbolic secant of u only if this would be 1. There's no negative here, class. Okay? Only 1. And in here also, let me just cross. So same here. So you have inverse hyperbolic cosecant of u over a multiplied to negative 1 over a, and the equivalent in ln. Okay? So many formulas. And we have to discuss but the last two, rationalization and method of partial fractions. Okay, you have this and have samples here. So there are 2. Read this. I will give you a problem set here, but it will be just short, maybe 1 for each of the functions. That way you will have a lot of time processing the exercises on your own and the examples which I haven't covered. The remaining topic class based on techniques of integration would be rationalizing substitution and method of partial fractions, if I'm not mistaken. So I will not be giving you any quiz next meeting because I need to cover all of this. Yeah, so it's method of partial fractions. Let me check if I still have. Okay, so none anymore. I think it's method of partial fractions that I have this here last because it's really very long. And it's a tedious process, so we need the 3 hours next week. Okay, so this will be included in your exam, but not anymore given as a quiz because we lack 1 week. Mayo time ito ang 1 week to a physical break, but we need it as well. We're not given. Okay? Any questions, class? Any violent reaction on the so many things that you need to study? Okay, inbox. This is an exam open-ended or multiple choice. Multiple choice. Why mark? Why? Okay. It's multiple choice. Exams are multiple choice. I only give open-ended quizzes because I wish to check whether my students would know how to solve without relying to choices that were provided. Considering the bulk of the topic in the exam, it's multiple choice. Any other concerns? So next week is our last lecture before the exam week, which is on March 14. Unless, as I've said, it will be moved. Any questions? I'll stop sharing.